Ladies and gentlemen, welcome back to Engineering Dynamics. In this video, we will be talking about an exercise regarding the rotor dynamics, where we will get the eigenfrequencies and eigenvectors and plot a Campbell diagram. Let's jump right in. So we have a special system where we have a rotor that is now supported at the hinge with a spring in direction X and Y, and not at the center of gravity where we had it the last times. So we have the coordinates X, Y, and Z. We have our given rotation speed. We have our inertia around X and Y and inertia around Z. That is the most important part for us. And that's all we need to know. We define the generalized coordinates, in this case, as psi-x and psi-y. In the last videos, we talked about how we do that with X and Y. So we get rid of the psi-x's and psi-y's, but in this case, we do it the other way around, where we have psi-x and psi-y as our generalized coordinates. To get the equations of motion, we first have to define the kinetic energy. That is a fairly complicated term, and it will get even more complicated, but we just ignore that for now. So let's take the kinetic energy as given, and also the potential energy as given. Then we have the equations of motion, where we get them with the Lagrange equations, where we have the time derivative with a partial derivative with our q's, or q dots, minus the kinetic energy derived by our q's, plus the potential energy, which is equal to non-conservative forces. In our case, we don't have non-conservative forces because we're just looking at how can the system behave on its own. If we do that derivation, we get two equations of motion, and these are the two equations. Now we introduce a new variable, IA, which is simply just mass times L squared plus the inertia around X and Y. The inertia around Z is its own variable, because this is the important part where the gyroscopic matrix will come into play. We can use these two equations and reformulate them into a matrix notation. So we will get the inertia. This is the part from the inertia. Then we have our gyroscopic matrix, that is coming from here. And then we have our stiffness matrix from these two parts. And they are equal to 0 because we have no conservative forces. So this is our mass matrix. This is our gyroscopic matrix that is dependent on our rotation speed, and the stiffness matrix. So first, let's look at the eigenfrequencies of our system where we don't have any rotation. So just the system on its own. So we're saying we have no rotation. That means omega is 0. And our G matrix, so our gyroscopic matrix, is then also 0. And we are left with this system. We use this Ansatz function, where we say that our q's in time are our x's, this is our amplitudes, and this is our time function. If we derive it once and derive it twice, we are left with this function. We have a I omega, so imaginary omega. If we multiply I omega with itself once, we get minus omega squared, because I squared is minus 1. Then we can reformulate our system, and we will get x minus omega squared m times our amplitudes, and we are not interested in the trivial solution. So one solution for this system is x equals to 0. So what we're saying is, well, if we're not vibrating, we don't have any eigenfrequency with which we're vibrating. So we're not interested in x is equal to 0. So we need this matrix to be singular. That means that it doesn't have a determinant. So determinant is equal to 0. And if we now use these matrices, so the M matrix minus omega squared, the K matrix, we will get two eigenfrequencies, which are actually the same. So we have a fixed eigenfrequency with multiplicity 2. And this is essentially like we had in the example. It is a mass supported by two springs with the same stiffness K, because we're saying that we have a support in X and a support in Y with stiffness K. The eigenvectors which we choose is that we can choose them as we want, as long as they're orthogonal. So we choose 0 and 1 and 0, and 0 and 1. So we have x1 and x2. So if we look at this system, so at the first eigenvector, it is basically a rotation around, or an oscillation in the x direction. So we move along the x direction. So it is a oscillation in the, we change our angle cx. So we change cx. So it is a rotation around x. So it is a rotation in the direction of y. The same goes for the second eigenvector, where we have a rotation around cy. So that means it's an oscillation around x. So if we have, this is our x and this is our y, and we have a, let's take the second one, we have a rotation around, or a vector around, this is cx and this is cy. So we're changing y. That means we're oscillating around this one and we move. So if this is our system, this is the rotor moves in the x direction. So now we're interested in, well, what eigenfrequencies does the system have if we're actually not stationary, but we are rotating? So to do that, we set our rotation speed to something non-zero, which means that we now have the gyroscopic matrix in our solution. We use the same ansatz function and input it into our equation, where we now have a I omega times g, which is equal to x times 0. We're not interested in the trivial solution, so that's why x is, we remove the x, and we will need to get the determinant of this function is equal to 0. To do so, or we use just a simple equation to get the determinant, and we will get a fairly complicated solution for the two eigenfrequencies, where we once have a plus and we once have a minus. So we see that we have two eigenfrequencies, one is smaller, one is larger, which will correspond to our forward whirl. This is the lower one, and to our backwards whirl, this is, the higher eigenfrequency is the forward whirl, and the lower is the backwards whirl. So if we now insert our equations back, into our eigenfrequencies back into our equation and solve for x, we will get two, again, different eigenvectors, which also are imaginary. So we have 1 and I and 1. But because we're talking about physical solutions here, we're not interested about the imaginary part. So to get the actual physical solution, we have our eigenvector times our function, our time function, and we multiply these two out. We multiply these two and only take the non-imaginary part, so only the real part. So cosine times 1, that's here. Then we have cosine imaginary, we ignore that. And then we have I sine times I, which is minus 1 times sine, and we get this vector. The same goes for the second one, which is minus sine, because we would have a I1 times cosine omega t plus I sine omega t. We ignore the cosine part, we only take the sine part, and for the lower half, we get only the cosine. And this will be our backwards whirl, and the second one is our forwards whirl. So what is the forwards whirl? Or let's go with the backwards whirl first. So we look at this vector. At time 0, where at x is equal to 0, and sine is equal to 1. So we're at this position. If time increases, our cosine decreases, so we move in the negative x direction, and because sine increases, but it has a minus, we go into the negative y direction. And we see that it will form a motion like this. And it is opposed to our rotation speed. That means if we're going opposed to our rotation speed, this is the backwards whirl. The same goes for the forward swirl, where we have a position for this is our time is equal to 0. And if we increase time, or time goes forward, we get a minus in the x direction. So we move in this direction, and a cosine in the cosine in the y direction, where we go down. Then we also can plot our Campbell diagram, where for a given rotation speed, we will get the eigenfrequency of the backwards whirl and the eigenfrequency of the forward whirl. So this is the backwards and this is the forward. And the backwards whirl will slowly approach 0, but will never actually get to 0. So we will always have a slight eigenfrequency that is going backwards and a very high eigenfrequency that is going forward. I hope this video gave you a better understanding on how to get the equations of motion for a system, then get the eigenfrequencies and the eigenvectors, see what is the backwards whirl and what is the forward whirl, and plot the Campbell diagram. If you have any questions, feel free to ask them in the comments down below. Thank you very much for your attention, and I'll see you next time.